Welcome to Everything Distributed. Today, I'm going to talk about proof of work. The content is based on BCT Chapter 2 and Bitcoin white paper. Recall that from last time we introduced the idea for hash pointer and blockchain, and from blockchain to Bitcoin, we need to answer how to order blocks. So before I start, let me explain to you in distributed system why this problem is non-trivial. Suppose we have 3 miners or 3 nodes. Each of them try to work out some block or some set of transactions. And because of asynchrony or because of failure, they will have different view when they want to exchange message or some kind of transaction. So for example, some people may say Lewis is awesome. So this miner receive a message saying this is good, but then this miner doesn't receive anything, so he or she doesn't know how Lewis is awesome. Or if you have failure, then suppose we have a Byzantine failure, basically it's a malicious one. He or she could do pretty much anything, and he just tell this miner say that Lewis is terrible. Then of course this is not very ideal. And that's the difficulty that we need to take up or take care of in distributed systems. Then in cryptocurrency, or like any kind of blockchain applications, why do we want to care about this in distributed system? Why do we want to implement this on top of distributed system? The first one is the notion of decentralized trust. It would be really good if I don't need to trust anyone, but somehow we can make something happen jointly, build something, trust out of nothing, and that's the idea for decentralized trust. And then the next one is auditability, meaning that once we agree on something, if someone tamper on something, then we should be able to detect it. So last time we talked about hash pointer and blockchain. The data structure can be used to address the auditability issue. And today we are going to talk about proof of work, how it is combined with blockchain to build the decentralized trust. And that is the foundation for most of the cryptocurrency systems nowadays. So now blockchain, now we have 3 miners, each of them has some blockchain to start with, and then they will work on something, and then the Bitcoin on very high level is actually very simple. It proceeds on a lockstep. It's a synchronous system or synchronous protocol. So in each round, nodes will exchange a block, and that's the process called mining, and then they agree on a block for the next one. So suppose the miners, each of them figure something different: green block, red block, and blue block. Why do we want to achieve agreement? Because if we have a disagreement on the block for the next lot, then double spending attack is possible. So suppose this red block is, let's say, Lewis pays Starbucks $10. And then this green block said that Lewis pay Amazon $10. Then if somehow the nodes, the miners, they don't agree on the next block, then Lewis can tell Starbucks, say, now look, the next one is the red one, so you owe me some coffee. And then tell Amazon, say that, hey, next block is a green one, so you should give me something. But then I'm spending the same $10 to 2 different entities and get the money back, or get a product back or coffee back. So this is not good. And this is why we want to have agreement on the next block, or more precisely, the next set of transactions. So how do miners agree on that? Then it's called Byzantine Consensus, because that in the world for Bitcoin, or in general, like permissionless system, anything can happen, and we could have a malicious behavior. And there are lots of different protocol called proof of something. So in this one, we call proof. We will discuss proof of work, but there's something like proof of ownership or proof of stake, and many kind of protocols. If you recall, for the FLP result, is that actually this thing is impossible to achieve if we have failure and asynchrony, which is that something we need to deal with in real system. So for Bitcoin or any kind of blockchain, actually they can only provide probabilistic guarantees. And we will revisit these ideas later. And from the book BCT, the mining step for each miner actually is pretty simple. First, you listen on the transaction, then you have your local blockchain, and you try to learn the new block. In the meantime, you assemble the transactions into your own candidate block. And then you want to find some nonce that make your block valid. Later, I will tell you what valid means. And then you broadcast your block, hope that your block is accepted. And then if your block is accepted, you get profit, which is a block reward and transaction fee. And before we go on, let's assume a very simple model, the peer-to-peer, and then the system is static, meaning that the participant, the set of miners, they don't change. And then each node has a way of communication. Let's abstract away from the networking layer, and then the nodes will use gossip to exchange message. And now let's assume that the network is synchronous. Then in Bitcoin, actually the consensus can be achieved in one run. And then the key for proof of work is step 4 here. So proof of work, like 3 steps. You start with your local chain, then you solve the puzzle. Remember, like last time we mentioned that one application for hash function is this like puzzle friendliness, and then that's the foundation for proof of work. And then later on, we use like gossip to broadcast the block that you find. And then the 5th one is that you check whether the block is valid, if all the transactions valid, and then you can accept it. Then you move on to the next round. So now let's look at each step more closely. So remember that each miner will have a local blockchain. And then you collect the transaction. Once you are happy, you form it as a block, and then the transaction will be ordered and will be kind of assembled using a Merkle tree. And then by link it, you create a hash pointer that point to the previous block so that you can ensure that you have a temper resistant property. And when we say that we are solving the puzzle for proof of work, is that like for given hash function, then we are going to find some nonce, the number that you are going to use only once, and then the hash pointer, you are concatenating all the field as a kind of binary string together, and then transaction 1, you block 3, transaction 2, you block 3, so on and so forth. And this is a one giant string, you put in a hash, and you get a value. And then there's a specified target for every miner. Then if you edge, this value is less than the target, or so-called mining difficulty, then you successfully solve the puzzle. And remember that because of the puzzle or the property for the hash function, actually it's very time consuming to find nonce, so that you need to keep trying on this nonce to figure out the value. And then that's the part that why Bitcoin is very kind of consuming lots of energy. And on the other point is that this hash pointer 3, I'm following the specification from the BCT book, but it has changed over time. If you want to know the most modern version, you can check the Bitcoin GitHub repo. It's all open source. Okay. Then the next one, when the nodes use broadcast, they use gossip to send a block to everyone once it successfully find out the puzzle. And this part basically that if you are not lucky, you keep trying, then you don't find it, you receive some other block from others, then you have, if you want to accept it, you start from that chain. Okay, we will revisit that idea later. But the whole idea for this proof of work is that you have on your chain, you create a new block, you solve the puzzle, and then broadcast to everyone. That's all. And before we do like a kind of more formal analysis, I want to share with you like why this thing is quite beautiful. The first is that from the Bitcoin white paper, the idea of this puzzle is essentially one CPU, one vote. Of course, right now, no one's actually using CPU to do the mining. People using the GPU, later on using the specialized chips because the CPU is too slow right now. However, back in the time, it's envisioned that you have CPU. And then the idea is that if you want to attack the system, then you need to spend something on your computation power. So there is some game theory involved to analyze that whether it is cost beneficial to attack the system or not. And then the other cool thing is that because of this puzzle solving thing, as long as you set your mining difficulty, your target correctly or properly, then it's a very well functioning permissionless system. So you don't need to keep track of identity. You don't need to do this current thing. You don't need to care about the vote because your CPU, your computation power is your vote. And then this mining difficulty can be adjusted. So it depends on like how fast people can solve this puzzle or jointly the system can solve puzzle. You can adjust the speed of like the generating a block. And then the security guarantee, again, depending on how many good computation power. Here, good, I mean that people following the specification of the protocol. And in the next lecture, we will analyze why this kind of design can prevent from certain type of attack and then what kind of security guarantee that it can provide. But that for now, just remember that this security guarantee is actually probabilistic because of the FLP result. So the takeaway is that like we describe the proof of work and then the Bitcoin one-run consensus protocol. So that's all. Thank you.